Welcome to my talk, Get Inspired by Web Development. And I would like to show you this based on the example of the Flux pattern. My name is Marius. I love to tinker with hardware and software. I'm also a Linux enthusiast. I contribute to the development of open source projects, which are mostly Linux-related projects. For example, Elementary OS, which is a Linux distribution based on Ubuntu. I'm the co-founder of SemaSquare. SemaSquare is a company located in Bochum, Germany, and we build software for embedded to web. You are probably wondering why I'm talking about web development at an embedded conference. Well, development in the web world is progressing pretty fast. It sometimes feels like a new JavaScript framework is released every day. We at SemaSquare try to use the best of the embedded and the web world. This allows us to unify the structure of projects in both areas. This also speeds up the onboarding of new employees. I'm sure you've also looked jealously at a feature from the web world. So why not get inspired and tailor ideas to your own needs? I would like to show you how to do that using the Flux architecture pattern as an example. For one of our customers, we developed control and graphical user interface for sweeping machines. A sweeper consists of numerous electrical and mechanical components that interact with each other. The components can be controlled graphically via our application. This HMI, a human machine interface, is programmed with C++ and Qt and runs on an embedded touch display mounted in the cockpit of the vehicle. The components of the sweeper also react to changes in state. For example, if the vehicle stops, some components are automatically switched off with a delay. So we were looking for a way to make the functions easily testable and the condition of the machine always predictable. And this is where Flux enters the stage. Flux is the application architecture that Facebook uses for building client-side web applications. It is a pattern to handle data in an application. And it was used at Facebook to synchronize the notification counter. The number of unread notifications is visible in many places on the website at the same time. And many users have raised bug reports in the past because the counters were not always synchronized. And because of that, Facebook developed Flux to ensure that data flows in only one direction through the application, as you can see here. The following slides should give you a better understanding of the data flow in the Flux pattern in comic form. The images used are from a blog entry called A Cartoon Guide to Flux, written by Lynn Clark, a software engineer at Facebook. So let's take a look at the different components in the Flux pattern. If you want to change the state of your application, you have to create an action first. This is where the action creator enters the stage. You tell the action creator what to do, and it formats the data so that the other components in the Flux pattern can understand it. And an action consists of a type and a payload. And once an action is created, it gets passed from the action creator to the dispatcher. The dispatcher keeps a list of all registered stores, and it sends actions to all stores, regardless if they are interested in the type, regardless of the type of the action. And the store holds all state of the application or part of the application, because there can be multiple stores. It then processes the actions and changes the state of the application or part of the application. It holds properties which cannot be modified, without dispatching an action. And the store gets all actions and filters itself which one it processes. And this is usually done by a switch statement inside a process function of the store. In an UI framework, the store then emits a signal, a change event, if the state has changed. The controller view is a middleman between the store and the view. It collects a new state from the store and passes it then over to the view. And the view gets a state and renders the user interface. So now that you have got to know the different actors, I would like to show you how the data flow works. So first, the user interacts with the application and would like to change the state. In this example, the user would like to be the middle number be changed to 10. So the view tells the action creator to prepare an action. The action creator formats the action and sends it off to the dispatcher. And the dispatcher sends the action to all stores. And the stores decide whether they want to react to the action or not. If a store has changed its state, it tells the controller view that the state has changed. And the controller view will then ask for the changed state. The controller view will then tell the view to re-render its UI based on the new state. This was a simplified graphical introduction to the Flux pattern. If you want to have a deeper look at this, you are welcome to have a look at the linked cartoon. Now let's get our hands a little dirty by looking at how to transfer the idea of the Flux pattern into C++. The following code snippets can be compiled, but are greatly simplified to explain it here in a nutshell. So let's start with an action. An action consists of the following properties. First, in type. And this is used in the stores to decide whether or not a store processes an incoming action. As I already mentioned, this is mostly done by the filtering by a switch statement inside the store. We also have a payload, and for now the payload is simply an empty struct. We also have a Boolean value that indicates if the action is an error. The dispatcher holds a list of all registered stores in form of an std vector, and you can register a store by calling register store. And if you want to dispatch an action, you call the method dispatch, and it iterates over all stores and calls a process message of each store, method of each store. And last but not least, we have the interface of a store, which only contains the method process, which gets an action and should process it. And an actual store would have to implement this method. So now let's dive into the code and see the components in action. So this is a pretty simple example. In our entry point of our application, we first create a bookstore. So this is an implementation of a store based on the interface we have seen earlier. And the bookstore looks like this. So we have a private property, an integer called number of books, which holds the count of books available in the bookstore. And we have only access readable via a getter to the value of the number of books inside the store. So we cannot modify the value from the outside of the class. Then we have the process method, which is passed an action over. And here we have our switch statement, which filters based on the type of the action and decides whether or not the store is interested in processing the incoming action. In this case, we have an action type we are interested in, and it's called add book. So we can add a book to the store, and all available actions are defined in enum. In this case, we are only capable, or applications only capable of adding a book to the store. And if the add book action is processed, the store simply prints out add book and the title of the book. And the title is cut out of the action payload. And then the store increments the number of books available in the store. So next, in our entry point for our application, we construct our dispatcher. And the dispatcher, on the dispatcher, the bookstore is then registered. So we can take a look at the dispatcher. We've already seen it earlier, so here's nothing new to see. So now comes a new component into play. It's called the book action creator. And so this is an implementation of an action creator. The book action creator is passed the dispatcher so that the action creator can format and then dispatch an action. And in this case, the book action creator has a method addBook where we pass the title of the book we want to add. So this is a book action creator. We see here in the addBook method that we can pass over a title in form of a std string, then create a book payload, and then we set the title of the payload to title, the parameter that was passed over. Here's the book payload struct. It inherits from payload and simply holds a property title. So next is the action is created. We set the type of the action to action type addBook and set the payload. And finally, we use a dispatcher to dispatch our action. So if we run our application, we first print out the number of books available in the bookstore. That should be equal to 0. We then dispatch the action to add a book with the title Flux 101, which would be processed in the bookstore. The bookstore should then print out addBook with the title, increase the number of books available in the store. And if we finally print out the number of books available in the store, it should print out 1. So if we run the demo, the printouts are as we expected. Yeah. So, as already mentioned, the implementation of the Flux pattern shown here is greatly simplified to make it easier to understand. And the execution of asynchronous tasks is not implemented in this easy example, in this basic example. And asynchronous tasks are not executed in a store, but in middlewares. And middlewares are also registered in the dispatcher. But they have also access to the dispatcher in form of action creators. And this allows asynchronous processes to be started by an action. And when the process is completed or there is progress, the middleware can again dispatch an action, which then flows through the application. And this way, a clear data flow is also guaranteed in this case. Okay, so as you have seen in the example, you have to pass a lot of objects around. And this is where dependency injection comes in handy. It works well in conjunction with Flux and also simplifies testing of some components heavily. For dependency injection, the following rules have to be respected. A component does not depend directly on the implementation of a class, but instead of an interface. Second, one or more implementations will then implement the logic of the interface. And the logic is then provided by one implementation to the component. For this to work, you need to create interfaces for all classes through abstract classes. This leads to some boilerplate code. But the effort is worth it, as you can also simplify testing considerably in this way. Because without dependency injection, testing of class A without class B is not possible. But with dependency injection, testing of class A without class B is possible with injected mock of class B. So here you see that you don't have to pass over class B in its entirety. For example, this could come in handy if class B would interact with the outside world. For example, with a web page, and in your testing environment, you are not capable of interacting with the outside world. Then you could simply inject mock of class B, which will give you the expected data, even if it's not interfacing with the outside world. And the effort for dependency injection can be reduced with a dependency injection framework, for example, like Google Fruit. Okay, using our onboarding project for new developers as an example, I would like to show you how Flux works in combination with the graphical user interface. So we use Visual Studio Code internally as text editor at SemaSquare. And we do this because its feature set can easily be extended with extensions. And we use CMake as build system. And the application itself is implemented with Qt and C++. For testing, we use Google Test to reduce the amount of boilerplate code when we are writing tests, because with Google Test you can use fixtures to, for example, define setup methods which are executed before every test in a test suite or test class. And to unify the build environment for all developers, we build and run our applications in Docker. Docker is a so-called container technology, which virtualizes an application on applications. It's lightweight form of a virtual machine where you not virtualize the hardware, but simply the software. And it's really great to use. And because our developers use Linux-based machines, developer machines, we can forward the graphical output of our applications through a Unix socket from the Docker container to the host operating system. And the user interface is then presented by the local X server, which then renders the UI. And this also ensures that all developers always use the latest build environment for the project, because Docker always checks if you are given specific version number of the Docker image you want to use, that if you will run a container, it will try to pull if there's a newer version available. And the project itself is controlled with a simple makefile to start the different tasks inside the project. Okay, so let's take a look at our application. As you can see, the application is built with make build and run with make run. So this is our application. It's pretty basic. We just have on the front page our logo, and in the middle a button to log in into our application. When we are logged in, we have simple layout. On the left side, we have a sidebar. This is a little bit inspired by the example I mentioned earlier at Facebook, where we have a notifications counter at different locations in the application. For example, here is the number of notifications print out. Here it is shown. And here is also a widget which would show the number of notifications, but only if the number of notifications is greater or equals to 0. Greater 0. Okay, so what we have else? Here in the top bar, we also have the git commit ID, which is print out so that you always know which version you are running. And in the middle of the screen, there's a content area where we have 3 buttons which can decrease, increase, and reset the notification count. And if I click a button, we dispatch always in the background an action which then is processed by a store and will then change the state of the application. So I can increase the notification counter. So now over here, there's also the widget shown because there are more than 0 notifications. I can further increase it. I can decrease, and I can reset the counter to 0. Okay, so we use this application or this base project to onboard new developers. So there are some bugs intently built in the application. So for example, I can decrease the notification counter below 0. And this is something that we want to fix right now. So let's jump into the code. Okay, if you want to get an overview what a Flux application is capable of, you can always take a look at the action types. And here we see it's a simple enum. And we have different actions we can execute on the application. And as you can see here, we have prefixed our actions with categories. So we have the category app, timer, language, theme, and counter. And as we want to fix our the logic which decreases the counter, we can simply copy this action type and search for it in our application. And as we have, as I've already told, mostly store or middleware filters if it's interested or not in an action by a switch. So we can simply look for action type counter, and here we see that it's only processed inside of counter reducer. A reducer is a more advanced component for Flux, which resides inside the store, so that the logic of the store can be broken down into subcomponents. So here we have the counter reducer. The counter reducer gets the counter model, and the counter model is a part of our store of the application. So we have mainly a hierarchical tree inside the application, and the counter model is one of the models. Okay, so we see that the process method filters the action type counter decrease, and then calls the method process decrease. So we see it's pretty basic. The process decrease method gets action passed over, and it then extracts the payload out of the action. It then gets the current count of the model, and then it finally sets the count inside the model, so also inside the store, to the current count minus the payload value. So we can not simply decrease by 1, but also by any value we want. So let's first write a test. Let's do it test-driven. And we see here that we have a should decrease processed test. And as I mentioned earlier, we use Google Test with pictures to reduce some boilerplate code. So all these tests reside inside the counter reducer test class. And because this is a fixture, we can implement methods, for example, setup. And setup is always called in every test case before the test itself is run. So there's always, if I call a test, always setup is executed first. So if we go back to should decrease processed, we see that we first call process increase. Process increase itself is a method of the fixture and increases the counter by payload, and the payload uses as number 42. So the counter would be increased by the value of 42. So we first arrange our components, then we act with in the test case and want to decrease again the count as a store. So we first increase it by 42. We then decrease it by 42, so that the count is expected to be 0. Okay, so let's create a new test which will check if we can drop below 0. Should not decrease. Below 0. So I can simply fire off this action 2 times. And if we now build and test our application, it should fail the test because the counter drops below 0. Yeah, so the test failed. And we see that the expected value was 0, but the actual value is minus 42. So now we can enter the counter reducer and simply say that the count should be the current count minus the value of the payload. And then we can check if count equals or greater 0. And then we will set the count. So if I now build and test the application, I hope that the test will be fixed. Yeah, this looks good. Okay, another cool feature I can show you is this. You can, over here, change the language of the application. So right now the application is in English, translated in English. We can also switch to German. And as you see, the texts are exchanged right now. And we can also change to pseudo. And I can tell you a little bit more about our pseudo language. Okay, so as you've seen, our applications are pseudo-localized. And we got the idea based on a blog post by Netflix. And Netflix UIs support more than 26 different languages. And they were faced with a problem that the expansion of text causes some UI elements to break. And most developers speak English, and so they only develop in English. And testing UI in different languages was done very rarely and not in the development cycle, or always in the development cycle. So they implemented a pseudo-localization. And you can think of it as a fake translation that remains readable to English-speaking developers and allows them to test for translation-related expansion of text, as you can see here. And we generate the pseudo-localization in our projects based on the English translations. And as you have seen in our base applications, the layout does not adapt to the expanding texts. So you can see here, so they overflow. And this is one of the tasks developers have to implement during onboarding. So this is, yeah. Okay, let us now look at the advantages and disadvantages of the Flux pattern. So pros, the structure and the architecture of projects are always the same, and developers can switch between projects easily. And also new developers can be onboarded quickly because of the same structure of the projects. And the origin of a bug or the place to implement a new feature is mostly clear to developers. And projects in web development have a similar structure to our embedded projects. And testing becomes very easy because all components of Flux are loosely coupled, and you can easily write tests if you have seen before. Of course, the concept of Flux must be understood once, and it can generate or need a lot of boilerplate code, but this can be reduced through tooling. And with Visual Studio Code, we use an extension called Code Templates. And I can show you an example for that. So if we jump back to our where is my mice? Yeah. Okay. So yeah, so I can simply call a new file folder from templates, and I'm sorry, wrong example. So if I call new file folder from template, we have a few templates based created. For example, for actions, DTOs, enums, middlewares, models, reducer services, blah blah. And we can create a middleware, and we just have to fill out some fields, and then the book middleware is created for us with a CPP file, a header file, and also simple test cases. Okay, I would like to show you next what is possible if you use the Flux pattern or even further extend by the Redux pattern. I can show you. Okay, so this is a simple to-do web application. And this web application is capable of adding simple nodes. So I can add a node 1, and a second node, and a third node, and a fourth node, and the fourth. And this web app is implemented in JavaScript with Redux. And Redux itself is based on Flux. And if I now show you the developer console, there is a tab called Redux. And here are the Redux dev tools. And as you can see, here are the actions which were processed inside the application. So whenever I entered a text and hit add, there was an action dispatched. So I can jump to the last action. I can show the state of the application in raw JSON JavaScript object notation, JSON. So this is the state of the whole store. I can also show you this as a chart, which is really nice. And I can also look at the action itself. So the action consists of a type, ID, payload, and completed. And it looks like this. So here the type is not number-based, but string-based or text-based. We have an ID and payload and completed, and in our examples, this would have been the payload. So this is only a different way of formatting the action. And what I can now do is I can do time traveling, which is pretty nice. So I can jump back in time to the point in time when this action was dispatched, so that now my user interface renders accordingly, because the state of the whole application was modified back to the time when this action was dispatched. So I can also jump forward in time, I can jump backward in time, I can jump forward but skip certain actions. I can re-add them. And what's also really nice, you can see here that the timestamps or the diff for the when the action was dispatched was recorded. So what I can also do is replay the state of the application. Yeah. And I think it's pretty nice. In this example or in this DevTools, it's always the same time difference between all actions, but you could also replay them accordingly in just the same amount of time they were dispatched. And we also already have translated this to our C++ code base. So we have a so-called logging middleware, and this logging middleware can already print out all actions. So because of the logic of the rules of the flux pattern, that all middlewares and all stores and all reducers get all actions, and they have to decide themselves if they want to do something with them or not. The logging middleware gets all actions and can then print them out. And we would like to expand it even further so that the logging middleware can also write an action to a file with a timestamp, the action type, and the action payload. And we would then like to implement a replay middleware, which then can be passed over the file, so that we then can replay actions that were recorded back in time, so that we could, for example, more easily debug a bug in the code or a bug in the logic of the user, which interacts with the interface, with the graphical interface. Or it could be also used for demos. So if you want to, or if you implement a new feature which is heavily UI based and you want to show it to the product owner, you can record the steps which are needed to show this feature, and then could simply replay it or send a recording of the state or of the actions, and then the product owner could replay the actions and so see the state and the UI acting accordingly. Okay, so I hope I could take some of your fears by getting inspired by the web world, and thank you for your attention.
Thanks for the talk, Marius. It is interesting to see how concepts from Facebook ended up in sweeping machines, maybe. Yeah. Who would have expected? We have some questions here, and I would like to you to answer them one by one. The first question: as compared to developing QML applications adhering to more classical QML interaction concepts, what is it like to switch to this concept coming from a C++ Qt world? You said yes, this is good for your new employees who know the web world, maybe, but probably you already had also developers that were developing embedded systems in another way, maybe more the classical way.
Yeah. So this is not such a big difference because you can write functions which are Q invocable. So you can simply call them in your UI in QML, and then these actions are dispatched. So it's pretty simple, or pretty similar to classic QML and C++ way.
Yeah. So we have another question that is similar to this. Often it is a good idea to have your business logic more on the C++ side than on the QML side. Would you say that this flux pattern kind of enforces you to more quickly go to the C++ side and do your actual business logic there, and don't do everything in JavaScript like on the QML side, which you shouldn't do?
Yeah, I think that the flux pattern heavily enforces this. And it's pretty great because you cannot access the properties in the store from QML, so you cannot write them, but simply read them. So you can simply, for example, create a list view in QML and show with delegates the list for the elements in the list. And if you want to add or remove an item from the list, you simply have to dispatch an action via a simple method call in QML. So it's pretty simple to do, and Flux enforces you to implement your business logic in the C++ area.
Mm-hmm. There's one of our viewers who is curious of performance impact of your Docker approach, where you say there's an extra connection through a local socket to the X server. Is there any performance cost here, or do you think that is actually kind of abstracted away and you actually did not have problems with this approach until now?
Yeah. So I have to clarify, this approach is only used for local development, and local development machines are often more powerful than an embedded device, so we don't have there any performance issues.
Mm-hmm. The last question we got was the code template you are using. Do they already contain tests or generate tests as well, or do you add them handedly afterwards?
So the code template tool or code template generation tool is pretty simple. So you have to write with a template in a template language. It's file-based, so you write a file and add your template code. And so if we want to generate a test based on a template, there are some pretty basic tests, but you need that. You have to implement the test on your own.